All right, hey everybody, Chris here. I'm here with my third and final dress shirt. I have to think more strategically about dress shirts when I'm in front of a green screen, but I think this one's working pretty well. Very, very blue. But today we're going to talk about oscillations and kind of things wiggling back and forth for the most part, and this is sort of the first in a series of lectures that's going to get us to the point where we're talking about waves, whether it's sound waves, light waves, ocean waves, who knows, earthquake waves. So that's kind of the unit that we're beginning now. Also, right now, you can start the final programming lab. The sixth programming lab is Planetoids with a Spring. And it's an interesting combination of the Planetoids with Momentum lab, in which you have this circle that that you can fly into and stick to, right? The blob. You fly into it, you stick to it, there's a momentum conserving collision. But your job is to connect this blob to a spring so that after the thing flies into it and compresses the spring, that there's a restoring force that pushes it back again, but then it keeps on sort of going back and forth. And so this is the last programming lab. I'm very proud of this programming lab. I think it's pretty fun. One of the fun things you can do is that once you're attached to this object, you can continue firing the thrusters of the rocket and to see what happens to the oscillations and things like that. So it's very fun, very interactive. I think you'll enjoy it. The coding is a little bit tricky, so send me an email if you have any trouble. But I think this is going to be a fun one for you guys. All right, so let's talk about this system. Let's talk about a mass on a spring oscillating. So this is an active figure from the book, which requires flash. So there we go. Here's what it looks like. So again, there's an object here, and depending how you set this thing up, it'll do some kind of oscillation. So if I press start now, it's probably not going to do anything because the initial velocity is set to 0. We've got a spring constant, that's fine. The position is 0, so if I press start now, my guess is that nothing's going to happen. Like so. Yeah, nothing happened. But if I take this thing and I sort of pull it this way, so I make the initial position, I kind of grab onto this thing and pull it over here, then it will oscillate. So I can do that, press start. Or I guess set and then start. Set. There we go. So I pulled it to the right, remember? I'm going to press start and you'll see that it kind of oscillates back and forth. And then I can also, instead of like kind of grabbing it and pulling it this way and then letting go, instead I can stick this back to 0 if I can. And instead I can give it some initial velocity. So I can give it, maybe I'll give it initial velocity like that. And now I can do set and then start. It'll look similar, but it's not exactly the same, as we'll talk about. But the main thing is that there's this kind of oscillatory behavior that we're going to study in just a moment. So that's the basic idea. Kind of the initial stuff at t equals 0 depends on whether it's the velocity that's starting it off or whether you're pulling it. So the other case, when we're pulling it, we started at some x. Whereas here, we started at x equals 0, but we gave it some velocity, and that's what caused it to oscillate. Anyway, there's different ways of kind of setting it up. Now, here's what we want to do, is we want to connect that motion with the things that we know about the system. So that includes, say, the spring constant, that includes, say, the mass that we're talking about, the mass that is on the spring. We want to know what that equation is. What is x as a function of t? And so what we're going to do is we're going to guess the functional form of x of t. It's always good to be able to be a good guesser. Doesn't always work, but sometimes it does. And what we can do is we can guess that functional form, and then we can substitute that into the relevant equations and try to figure out the variables that are there. So to guess the functional form for x of t, well, first let's write down the relevant equations. So this is what I call the natural length or the relaxed length of the spring. It's not the same thing as the equilibrium length, because if you hang this thing vertically, gravity will pull on it, and then it won't sort of hang out around here. It'll be some other value, but when it's on its side, this is the natural length of the spring, and then this x is the distance from here, basically. So there's a restoring force there. The thing to remember is that if your coordinate system is like this, and if positive x is this way, then when you're taking this block and you're pulling it this way, well, then the restoring force is to negative x, right? And so if you think about this equation, x here is going to be greater than x natural, and so x minus x natural is going to be positive. And so if we didn't have this minus sign here, that would indicate that the force of the spring would be this way, which doesn't make any sense. It makes much more sense if the force of the spring was back towards that, was towards this thing, to negative x when you're extended this way. So that's why this minus sign out here is important. Sometimes I'm a little sloppy about this minus sign, but it does deserve to be there. So this is one of the equations that we're going to have to deal with. Now, in this case, the only force is the force of the spring. So we're going to neglect friction. Don't worry about friction for now. It's not a rocket. We don't have to worry about rocket thrust or anything like that. So this is the only force. And so the sum of all the forces in the x direction just give you the force of the spring. And so that equals the mass times the acceleration. Now, the acceleration is the derivative of the velocity per unit time. And so we get this. But remember that the velocity is the derivative of the position with time. And so you can also rewrite it like this. And so when I come up with a formula, which is another way of saying the second derivative of x. So when I come up with a formula that I'm going to guess the functional form of x, it's got to be able to kind of solve this, this thing combined with that thing, if it makes any sense. In other words, this equation. So this is the equation that governs the system. The thing to bear in mind is that this has time dependence. This x has time dependence. This x does not have time dependence. The mass does not have time dependence. Also, the k constant does not have time dependence. So for example, I can rewrite this thing like that, and that is perfectly true, right? So that's time dependent. Here, this is time dependent. Nothing else is time dependent. So I have to guess the functional form of x of t. So I'm going to do that. Now we know it's oscillating. We know that there exist sine and cosine functions. We don't really know 100% for sure if it matches this situation just yet, but at least by eye it seems to work. Let's say, like when you do a real system and you say, yeah, that looks like a sine or a cosine, then that's enough. At this stage, that's enough of an excuse that we can use these functions to do what we're going to do. We could use a sine wave. We could use a cosine wave. I'll talk about that later. I think we're going to use a cosine wave. No, we're going to use a sine wave. All right. We're going to use a sine wave to model this motion. In a few slides, I'm going to use, I'll show you how it relates to cosine waves. But what we're going to do is we're going to say, all right, well, it sort of looks like this, kind of, sort of. We know the sine function is oscillating back and forth. We know there's some overall value of this thing, which is c. And then we know there's some amplitude of this thing. So maybe it's a little tiny oscillation. Maybe it's this mass on a spring is wiggling just a little tiny bit, or maybe it's wiggling a lot. There's some amplitude associated with that motion. So what we want to do is we want to put this in the equation. We want to try to solve for a, b, and c out of this as best as we can. And so we're going to stick this into the equations I just showed you. Again, I'll talk about the cosine case later on. So here we go. We're going to sub this into here. In a second, I'll have to take a bunch of derivatives of this thing. So all right, so there I did. I subbed our guess into here like this. Sine bt plus c, same thing over here. And so this, we can take some derivatives of this, right? So it's a second derivative, and so I can take the first derivative of this stuff and then do the derivative of that again, right? And so here's the thing though, is that the c is constant. A, b, and c are all constants. They do not change with time. And so what is the derivative of a constant? I'm listening. Derivative of constant is just 0, so that gives you 0, right? And then we're left with the derivative of a sine function, right? So the derivative of a sine function is just cosine, right? So the constant comes out, right? And then this derivative is just cosine bt, right? So the b came out, right? Because of, I think it's the product rule, chain rule, product rule, one of the rules. So the derivative of sine is a cosine. And now we have to do it one more time, right? Because it's the derivative of cosine. We know what that is. First, I think we're probably going to take these constants out front, probably. Right? There we go. Derivative of cosine, well, derivative of cosine is negative sine. Right? And so the same thing's going to happen, and we're going to get an extra factor of b out here because of the product rule. And so we have shown that this thing here, in other words, this thing here, works out to be equal to this thing here, is what we've shown. So this somewhat scary-looking thing turns out to be not quite as scary-looking of a thing. So now I can put it all together like this. So this is what we get. Now there's an interesting thing we can do here because this equation is true at all times t. And that's a very useful thing to know because it means that for any time t that we choose, this equation has to be true. And a particularly interesting time to think about is when t equals 0. So sine of 0 is what? 0, right? So when t equals 0, sine of 0 here is 0, sine over here is 0, and we're left with something that's quite a bit simpler, right? So we're left with this, and the only way, the only way that c minus natural length equals 0 is if c is equal to the natural length. So again, this formula that we've guessed, the c part of it is not too bad. Okay, we figured that out, and it kind of makes sense, right? It was going to oscillate about this natural length anyway, and so it kind of makes sense that this c is the natural length. So I can stick that into there. Boom, there's that. And so that's going to simplify down. And we can simplify this further. I always forget what the next step is, but we can simplify this further. We can multiply both sides by -1. We can divide by a, things like that, divide by the sine function. So there we go. So we're going to divide by the sine function. We end up with this. And you see there's an a on both sides, so we can divide both sides by a. There's a -1 on both sides, we're going to multiply both sides by -1. Right? So go from this to that. And we can solve for b here. So we can divide both sides by m. Take the square root, we can conclude that b, the thing that goes inside of the sine function, is equal to square root of k over m. Okay, so we're on our way. So we know that b is equal to this, c is equal to the natural length. This is what we get from what we've done so far. So that's pretty good progress, I feel like. By the way, the fact that the time dependence cancels out here is the key thing that we've made a very good guess at what the sort of at our little function here, the sine function. If that hadn't happened, then this whole rest of the analysis would not have gone so well. All right. So now that we have this function, which is here, we want to look at this function. We want to figure out what is the period of the oscillation. First question is, what is the period of oscillation on this plot? Is it here to here? Is it here to here? Is it here to here? Things like that. Is it peak to peak? What is it? Well, there's a couple different ways we could have defined it, that physics people could have defined it, but here's the thing, is that this is only halfway through the cycle. A period is the full cycle. And so if we started here, the next cycle would begin about here. And so that means that this is the period, not like just from here to here, if that makes any sense. So this is the period, right? It so happens that this distance is the same as this distance. So that's also the period there. And we ultimately want to figure out what is this period in terms of things like k and m and whatever else we can think of. Well, the thing to remember is that if you compare to a sine function, here's the question: at what angle does the sine function equal to 0 here? Sine theta equals 0. Technically, the sine theta equals 0 here, but that's not what we're interested in. We're interested in sort of the second time it hits 0. So if you think about it, and you can kind of see from my axes here, I have, 6 here. So 2 pi is pi is about 3, so 2 times 3 is about 6. So this is 2 pi when it equals 0 here. This is sine equals pi. This is sine equals 2 pi. So whenever the thing inside of the sine function is equal to 2 pi, some would say the argument to the sine function is equal to 2 pi, well, that tells us what the period is. So what I can do is I can take our this formula and I can say, all right, well, at what time t does this equal to 2 pi? And so we'd end up with something like this, right? And we know that that's the full period, and so that time t is the period, the capital T. And so I can solve for that capital T. So I can multiply both sides by square root of m, divide both sides by square root of k, and that gives me my period. So we figured out, not only have we figured out the mathematical equation describing the motion, we've also figured out how the period of that motion depends on the mass and depends on the k constant of the spring. So now that we have the period, we need to figure out what the frequency is. And so we can do that. So if you remember, the period is the number of seconds per cycle, right? How many seconds does it take to make one cycle? Whereas the frequency is the number of cycles per second. And so if the period is very, very small, then it might be multiple cycles per second. And so that's an inverse relationship. So the period is 1 over the frequency, and the frequency is 1 over the period, right? So here's the frequency, 1 over the period. We've just determined that this is true. So if this is true, that means that this is true. And so that's kind of what we get from it. Now what's interesting is that if we write the angular frequency, well, the angular frequency is 2 pi over the period. And so you stick that into, we figured out the period up here, so you get an extra factor of 2 pi up here. And so the angular frequency becomes just square root of k over m. So it's very elegant, very simple. There's no factors of pi or anything. And so often we will kind of write this equation this way. Amplitude sine omega t plus, whatever the equilibrium or natural length is. And we'll try to solve for this omega. Now, the reason I didn't use this symbol before is because if I start using omega, you'll assume that it just has to be this way. I wanted to kind of show you where it came from, instead of sort of, in rhetorical terms, it's called begging the question, that it just sort of had to turn out to be in some way. So in any case, the things, this is a very elegant kind of way of thinking about it, is in terms of angular velocity, angular frequency. In other words, this is why we do this in the first place. This is why we don't just do F all the time. It looks more elegant this way. Elegance is important, people. It's important. Now, I promised you that I was going to explain why we didn't use cosine in the analysis. The analysis would have worked fine with cosine, right? Because the second derivative of cosine is minus cosine, and so the same kind of thing would have happened before. Sort of a more general thing that we could have done is if I would have put in a constant phase to the sine function, which you'll need to get some practice in doing for the homework. But if I gave a constant phase function to the sine function, then I can turn this into a cosine function if I just change that phase to pi over 2. And so you can notice that you can do the whole analysis again. You get the same thing. The second derivative of this thing is equal to minus sine omega t plus phi, the phase. So the whole analysis works both ways, which means that you can do it with the sine, you can do it with the cosine, you can even do something with sort of in between with this function. And it all depends on exactly how do you start this thing oscillating. Do you start it by sometimes say flicking it. So it starts from the natural length, but you give it some initial velocity, or do you grab it and you pull it and you let it go? Those things all go into what exactly is this phase factor. All right, so now that we've talked about oscillations in the horizontal direction, it's important to talk about oscillations in the vertical direction, because we cannot just assume that the period of oscillations in this case is the same as it is for sort of the sideways case, because gravity could change some things. I don't know. We'll have to see what happens. So what I'm going to do is I'm going to say, instead of having x be our horizontal variable, I think I'm just going to try to make our lives easier and say that plus x is up. I could change it all to y, but I feel like it makes it look more weird if I change it all to y. But yeah, plus x is up, minus x is down. And so as a result of that, we can keep this. We do have to add one thing to it, right? Because we have to add gravity. So if you remember where this side came from, this was the restoring force of the spring. This was the mass times the acceleration. Well, the mass times the acceleration, that part's the same. But we have a gravitational force that we have to add over here. And so we can do that. So we have the restoring force of the spring, but then we have the weight pulling down with the constant, which is just mg. And so now we have something that's very similar to what we had before, except for this minus mg. And so what we can do is we can solve this equation again and see what we get. Again, try to solve for the a, b, and c, and just see what happens. We might get something different, it might be similar, we'll find out, right? So let's see, all right, so again, I'm trying to solve for a, b, and c. But now there's this minus mg thing here. So as before, this, I don't have to go through this again. I know that this turns into something relatively simple, which is this, right? I can take the second derivative. The sine function gets something like this. Now remember, at this stage last time, what we did was we said, well, this equation is true for all times t, which means that it is also true at t equals 0. And so I put in a t equals 0 here, and the sine function goes to 0, right? Because sine of 0 is 0. Same thing over here, sine of 0 is 0. And so now we end up with something like this, right? Because we still have the mg here, right? The weight is still the weight, even at time equals 0. We have the c minus the natural length. We have the k constant here. And this thing, and this thing add up to 0. So we can solve for c. And so I can do that. So add mg to both sides, divide by k, add the natural length. You get something like this, right? So when the gravity is equal to 0, c is equal to natural length, which is good because that's what we came up with before. But for non-zero gravity, you'll find that the place where the thing oscillates is a little bit lower in x, more negative, than it was before, and that's simple to understand because gravity is pulling it to be more negative, right? So this has changed. The question now is, has other things changed? So for example, has the period changed or not? Let's find out. Okay, so now we have this. I can stick it back into here, right? So I can stick what we just learned into here. And then the natural length is going to cancel with the natural length, which is what happened last time, if you recall. A new thing is this term here, but minus k times minus mg over k equals plus mg minus mg just equals 0. And so we end up with something we basically get back to where we were before. And we divided through by the sine function. We divided the amplitude. We multiply both sides by -1. We end up with this. So this is the same thing we got before. Again, not obvious at all that this frequency is going to be the same, but it turns out that it is. So gravity apparently does not affect the oscillation frequency for a hanging spring, which is interesting. So this ends up being the formula for a hanging oscillating spring. And you can kind of see that the period would be the same. As long as B is the same, then the period. Here's kind of an example question that you might see on maybe the final or something like that. I'm thinking about how does the oscillation frequency relate to, say, the K constant of the springs. So I have this animation here, and there's a spring on top that's oscillating. That's one spring. And then there's two springs down here. Now let's say that the springs, all three of these springs have the same spring constant. And the question is, how does the period of this one relate to the period of this one? And let's say that the mass is the same. Okay? So let's think about this thing. So when you add the second spring, does the oscillation frequency increase, decrease, or stay the same? Take a second to think about this. An internet second, perhaps, but a second nonetheless. All right, so you add the second spring, the oscillation frequency. Well, there's more force going on, and so, but the mass is the same, so it should accelerate more quickly, and that should cause it to move more quickly. And if it's moving more quickly, the frequency should increase. Okay. What about the oscillation period? So again, we've added a spring. We just convince ourselves that the frequency is faster. So what does that do to the oscillation period? Think about that for a minute. So the frequency and the period are related, right? So the frequency is the number of cycles per second. The period is the number of seconds per cycle. And so the period is 1 over the frequency. So if the frequency is getting larger, then the period is getting smaller, and so the period has to decrease. Now here's a trickier one, which is to say that if we had one spring and the period is T1, and then we use two springs, again it's the same mass, what happens to the period in that case? So what do you guys think? I'll give you a minute to think about it. So here's some thoughts on this. So first of all, we decided the period is not the same, so probably not C. We decided that the period of two springs is going to be smaller, so probably not B or A. So we're down to D, E, or F. But let's think about this for a minute. Okay, let's take a look at this and see how the period changes when we add a second spring. So here's our two springs. Let's think about spring number 1, which is sort of this one here. Now in this diagram, as you can see, spring number 1 is in tension. So the object is sort of off to the right. The natural length is sort of here, right? And so the object is over here, and so the spring is kind of pulling it back this way. So in terms of its position, this would be its position. So the spring force would be something like this, right? So it's the difference between the position of the object and the natural length. So here, x is larger than the natural length. So x minus the natural length is a positive thing inside of those parentheses. But then there's always this minus sign in the restoring force, because if it's positive displacement this way, then the force will be in the negative direction, and so that's why that minus sign is important. And so just to make this all slightly simpler, we can say, well, there's here there's this delta x, and so it's displaced from the natural length by this much. And so the spring force is basically the K constant times that much. And so if this is positive, that's negative, so this is to the left, as you can see from the diagram. So again, this is just from one spring. Now let's think about the other spring. So this spring is in compression. So its natural length is, something like this. And we could give a lot of thought of trying to figure out how the spring force works here, but suffice it to say that this object is displaced from the natural length by the same amount. And so this spring, because it's in compression, it wants to push the object away. And so that force is spring constant times delta x. Again, that's how far it is from the natural length. And then that's to the left, because you can see from this coordinate system here that, this way is positive x and that way is negative x. And so this is clearly trying to push it towards negative x there. And so there's two forces, and we can add those together to get the net force. So force of spring 1 plus force of spring 2 is going to be twice that k constant times the displacement from the natural length. And of course it's leftward, and so we're going to put a minus sign here. So this is gets us most of the way to our answer, because the key thing to realize is that adding a second spring is basically just doubling the k constant. So this is our situation with just one spring. If this was the angular frequency, then in this case, where there's two springs, there would be twice the k constant inside of this thing, but it's the square root. And so that means that the angular frequency goes up by the square root of 2 when there are two springs. And so now that we know that, we can figure out how the period changes. Now the period is this, right? So if it was one spring, it would be like this. But if it's two springs, well, then that's twice the k constant, which means that this period now that there's two springs, is going to be T1 divided by the square root of 2. Which is why, the options I gave you on the multiple choice, none of them would quite work, because we had to think about this carefully. Okay? So the next thing to talk about is damped oscillators. And this is, every system has damping on some level, and we've been ignoring it up to now. But as you can see, this thing will slowly come to a stop. And I like looking at this thing because you can see the acceleration, have a nice little sensor on there. But eventually this thing will come to a stop, as you can see. So we haven't really thought about this yet, but it's an important thing that we should think about. And so we're about to have an adventure in understanding damped oscillations. It's going to get interesting. All right, so first of all, there's multiple different sources of friction. We've already talked about kinetic friction, way back at the beginning of the course. I may have mentioned air friction. Sometimes I give extra slides for that, sometimes I don't. But that's another source of friction. But the friction we're mainly going to talk about today is the friction due to a so-called viscous fluid. And so an example of that is putting an object in water. So I don't know if you guys have ever seen those exercise bikes where your legs move these paddles around a water. Well, water is a viscous fluid, and so the energy of your legs gets used up sloshing around the water, and so that's a form of damping. Well, regardless of which one of these sources of friction that we're going to consider, how does it change this equation? Because this is the equation that we were worried about before, right? And if you think about how this equation came about, this is the mass times acceleration here. That doesn't really change. But this came from the force. So this came from the fact that there was just the restoring force of the spring before. And if you remember, when we added gravity to it, we just added the weight here because it was just another force. So if we're going to add the friction, well, then we'd have to add another force here to represent the friction force. So that's all we really have to do. And so on the next slide, so what exactly does the friction force look like? In real life, there is, it's always good to show you guys what the real life thing is, and then I can do the tremendous oversimplification of it. But in real life, real objects above a certain speed, don't quote me on this exact speed, it depends on the size of the object. But above a certain speed, the drag force goes as velocity squared. So this is normal drag. Sometimes I call this air drag. But below a certain speed, the air drag goes more proportional to v. Now, that doesn't mean that there isn't a viscous drag when you're going really fast. There still is a viscous drag. You can see this dotted line continues, and that adds to the drag just a little bit for the total drag force. You can kind of see this little dotted line, that's the v squared. So, I mean, it increases the total drag force slightly, but if you add the two of them together, at the end of the day, this is very, very small compared to the v squared, right? Again, the dotted line that goes all the way up. And then at low speeds, the v squared is very small, right? Because if v was 0.1 and you square it, that's 0.01. So it gets smaller, right, as you go to lower speeds. So at the low speeds, you end up with sort of a linear drag, linear with the velocity, whereas the higher speeds, you go as velocity squared. So for cars, for example, when you're on the highway going 60, 70, 80, 90, who knows, 150 miles an hour, that's very fast. And so the v squared is what matters there. But if you're going very, very slow, or if you're going in a very thick fluid, like honey or something, or oil, it's really the viscous drag that matters. So most of the time in engineering situations, the v squared is kind of the more important one because, there's a lot of air to think about. But for our purposes, we're going to focus on this one because it's a little bit easier to handle mathematically. So this is the viscous drag. You can see this gentleman putting this little weight in water, watching it go up and down. So there's a drag force there, and over time this thing will come to a stop, more or less like that other thing did, except it was going horizontally. But what's nice about it is that this is the formula that determines it. So this b is some constant for whatever situation you're thinking about. But the larger the velocity, the more the force to slow it down, if that makes sense. And so if you want to add this to as a force, well, then you would add it over here. It still equals the mass times the acceleration. It turns out that this equation is solvable. And we're actually going to solve it today, believe it or not. It's going to be a bit of an adventure. This is one of the active figures from the book, which I think is pretty good. You may or may not be able to use this on your own device. But the nice part about it is you can kind of click this thing and pull it down and then let it go and watch it kind of oscillate there. Now right now the damping is at 0, but if I turn the damping on, if it's going to let me do that, turn the damping on, let me do it like here, and I do the same thing, maybe I can pull up on it, I don't know. You'll see that over time it peters out. It depends on the drag. This is that constant b on the velocity. So that's the basic idea. It's kind of a fun demo there. So if you remember from before, we sort of guessed the answer and then we tried to determine those constants. So we're going to try to guess it again. It helps to be a good guesser in this business, but let's guess something at least quasi-reasonable, which is that there's some oscillating term, and let's say it's a cosine. By the way, it's a little bit important that we use a cosine instead of a sine because at t equals 0, we kind of want this thing to be displaced, right? Because I took that block and I lifted it up or I pushed it down. Cosine is going to be a little bit better for that, right? Because sine of 0, it's just 0. So let's go ahead and use a cosine. That seems reasonable. There's some amplitude, right? So it might be a lot, it might be a little bit. And then there's this function that the key thing about this function is that when t equals 0, it needs to equal to 1. But when t is very large, it ought to be equal to 0 because everything is all damped out. The other thing that we know about this function before we do anything is that if b is equal to 0, well then this function had better be equal to 1 for all time, including infinite time, right? Because there's no damping. So that's what we know about this function. This function is often called an envelope function because you can kind of look at this curve and say that there's sort of a trend, like peak to peak there. There's kind of this thing wiggles between, some function that is this f of t. So what we want to do is we want to figure out what this f of t is. We want to figure out what A is, we want to figure out what B is, and we want to relate as much of this stuff to the mass of the object, the damping, and the K constant. One thing you may have noticed is that we've gotten rid of like the plus a constant thing because we're going to assume that things oscillating around 0. I could have put that in there if I wanted to, but I thought it was just a little bit simpler to leave it out. All right, so again, the mission is to try to figure out what is this constant here, B, what's A, and how does f of t relate to, say, like the damping. Okay, so we know the function has to have the form, and we're going to make another particularly good guess, and we're going to say that, well, it would make sense if this f of t had this kind of behavior, right? So some exponential times a constant times the time. And the reason this equation makes sense, and we'll find out if it actually makes sense, but the reason this equation makes sense, at least on the face of it, or that it's a decent guess, is that we have this requirement on the function that when t equals 0, this function equals 1. Well, e to the 0, right? When t equals 0, that's e to the 0. Anything to the power of 0 is 1, right? So check on that one. And then if t is very, very large, well, that's 1 over e to the c to some very large number. Well, eventually that's going to trend to 0. And so for t very large, this equation that we're guessing does indeed trend to 0. Okay? So what we're going to do is we're going to calculate. The first thing to do is to take this and to calculate, well, if this is the formula, what then is the velocity as a function of time, what then is the acceleration as a function of time, and then we can try to put it all together and figure out what these constants really are, which is what we're going to do on the next slide. Okay, let me just double check this is recording. Good, all right. Okay, so the velocity, so all we got to do right now is take the derivative of this expression, right? So we're going to take the derivative of this thing, and we can use the product rule. And so the product rule is, the derivative of this thing times not the derivative of that. This thing equals the derivative of this thing times not the derivative of that thing plus the derivative of this thing times not the derivative of that thing. So something like this, right? So there's two terms here. Right, so in this one we did not take the derivative of the exponential, whereas this one we did, which is why there's a c out front. So this is what we get for the velocity. And we can simplify that a little bit if we factor out the a and the minus sign and the exponential. So unfortunately, that's about as simple as that one gets. The next part is this is probably the worst of it, but we have to take the derivative of the velocity we just figured out to figure out the acceleration. So we're going to take the derivative of this thing, and so now we're going to do the product rule all over again with more terms. And so it's going to get a little bit messy there, but hang in there, we'll get through it. There's pets in the room. There's 2 pets. There's a dog here, there's another dog there. We'll be fine. They're very cute. So when you work this out, you do the product rule, you say, all right, well, the derivative of this thing times not the derivative of this thing, which is this one, plus not the derivative of this thing times the derivative of this thing, right? And so when we take the derivative of this thing, well, the derivative of cosine is negative sine, which is why that's there. The derivative of sine is cosine. And the b comes out, right, because of the chain rule. So this is what we get for the acceleration. We might be able to simplify this just slightly to that, right, because I can factor out the exponentials again. And so now we have this, and again, unfortunately, it doesn't factor any better than that, but that's what we get. So now we have the position, we have the velocity and acceleration. We can kind of put this stuff together. And what we can do is that because that equation of motion, that equation we're trying to solve is true for all times, including t equals 0, that means that we can look at these formula and see what they are at t equals 0 and maybe learn something. So if you think about t equals 0, well, cosine of 0 is 1. And then e to the 0 is 1, so that just equals a. Same thing here. Cosine of 0 is 1. Sine of 0 is 0. E to the 0 is 1, so this becomes minus ac, because there's a c constant here. And then the same kind of song and dance here. So this sine term is going to be 0, but the cosine term is going to be 1, and so this acceleration simplifies to that. And now, we can go back to that, the equation that we're trying to solve, putting it all together, right? So this one. And so when we stick that in here, well, at t equals 0, x is equal to a, right? At t equals 0, the velocity equals minus ac, and at t equals 0, the acceleration equals this. So we can stick that all into there, and then try to see if we can make headway here. There's not a ton we can do with this equation just yet. This is going to be very useful later. But one thing we can do is we can divide by the amplitude, a. So that divides out. I think we can also multiply both sides by -1 maybe. Anyway, so this is about as simplified as this one's going to get. So this is still interesting, believe it or not. It's interesting because if we can figure out either what b is or what c is, it helps us to figure out the other one. If I can figure out c, then I can figure out b. If I can figure out b, I can figure out c. Because I know the rest of this. I know the mass, I know the damping, I know the k constant. So this actually gets us further than we had been. So b and c can't just be anything. They have to be, they have to follow this relationship. So that's useful. All right, so we'll come back to that in a second. The next thing we're going to do is pretty clever. This is actually kind of clever. So I don't know what b is, right? This is kind of a trick we're going to use. I don't know what b is here, and I don't know what b is here. I'm trying to solve for b, for goodness sakes. But I do know that if t equaled pi over 2b, then I would have cosine of pi over 2 here, which is equal to 0. Same thing with the sine function. If t is equal to pi over 2b, then that gives us sine of pi over 2. Sine of pi over 2 is 1, right? Pi over 2 is 90, so sine of 90 is 1. And so if I don't even know what time this is. I just know that at some time, there should be some time for which t is equal to pi over 2b, such that this cosine would be 0 and the sine would be 1 because of the way this is constructed. So this is kind of a clever trick that you might not have thought of, but we're going to use this to great effect. Okay? So let's use this with our formulas. So use it in here. When t equals pi over 2b, well, this cosine is 0, right? So these are all 0. And then these sine functions are equal to 1. And so here I get x equals 0. I get v equals minus ab times 1 times the exponential, like that. And remember that our time is equal to pi over 2b, and so the e to the minus ct ends up being like that, right? Because we're subbing in the value for the time. And then our acceleration down here, we can kind of do something similar. Again, the sine term is equal to 1, and we know that this time is equal to pi over 2b. So this is kind of a clever thing, right? At this time, whatever this time is, this equation is true because this equation is true for all time. And so at this time, x is equal to 0, but the velocity is equal to something, and acceleration is equal to something. So right, so x is equal to 0, don't worry about that. Here's the velocity, here's the acceleration. So I can simplify this, get rid of that thing because it's equal to 0. I can divide both sides by a, And what else can I do? I can divide the exponential on both sides. There you go. And multiply both sides by -1 maybe? No, divide by b. Sorry, I can't remember which one's which. Divide by b, that's fine. Now multiply by both sides by -1. We get b equals twice the mass times c. Again, this is the damping. This is the little b. Basically what this means is that c is equal to the damping divided by 2m. We know what the damping is. We set up the experiment. We know what that damping is. It's written on the thing. I don't know. We know the mass of it because we can put things on a scale and measure that. And so we figured out what c is, which is one of the things we really wanted to do the most. We figured out what it is. The last part is figuring out what this capital B is. And we don't have enough information here to figure it out, but that other equation that I said was going to be useful in a minute, well, now we can use it. So if you take this equation, which we found earlier, and you substitute into it that c is equal to b over 2m, well, now you have an equation that you can solve for this capital B thing here. And when you do that, you find this. So I'll spare you the slides of algebra, but I think you can take my word for it that you get a b squared over 2m here because it's b times little b here. You get k over m. It's pretty straightforward to come up with this. So this is what you get, and it's important to talk about what this means because this is kind of interesting. So at the end of the day, you end up getting this sort of a thing again. So e to the minus this b over 2m times the time. Time's out on the top, by the way, not on the bottom. And then the cosine term is going to oscillate according to this thing. So the cosine term is not oscillating according to square root of k over m. Instead, it's oscillating according to square root of k over m minus this damping thing. So this is very interesting because if you think about what this means, is that b is sort of this angular speed. It's how many radians per second. I mean, it's how quickly are these oscillations going, right? The larger the b is, the more quickly the oscillations go. And so because there is a minus sign here, that means that this damping is slowing things down. It would be a little weird if the damping sped things up, wouldn't you agree? And so things that have damping are going to go more slowly. So for example, the speakers in your sound system, when you put those up to full volume, they start rubbing up against things that they didn't before, and there's sources of damping that used to be small when the amplitude was small, but when you're cranking up as loud as you can because you're trying to see what your stereo can do, the damping becomes important. And as if you have a stereo like that, you know that if you're going at absolutely max volume, it's going to change the pitch a little bit, especially when it gets loud. And so you can, if you have good enough pitch, you can hear that happening. I mean, you can also analyze it with your phone if you want to. But yeah, the damping is going to slow down the oscillations, which is interesting. It's also kind of interesting because earlier we were talking about how if you hang this mass from the ceiling and there's no damping, that you wouldn't necessarily expect it to have the same frequency as if this thing is oscillating like this, but it does. So here, who knows what we would have gotten? We might have gotten square root of k over m again, but it turns out we don't. It turns out that the damping actually does affect the oscillation speed, which in some situations could affect pitch or something like that. Another interesting thing is that if the damping is equal to 0, you still get square root of k over m, which is what we got before, earlier in this lecture. So it all kind of makes sense. I mean, there's a lot of algebra there, but the result that we get is not super crazy. Again, what I did was, instead of just assuming that there's an omega here, I did sort of an ABC thing because I didn't want to pretend like, oh, we all know that omega is going to be whatever it is. We're just solving for this constant. So most people would use an omega there. But whatever. All right. So let's think about the different kind of behavior that this equation can give. this equation with this equation, right? Because this capital B appears in here. So let's think about the different things, kind of behavior that we can get from this. It turns out that there's three different kinds of behavior that we can get from this. And what's interesting is that it does not really depend on the size of the spring system. So you can have overdamped oscillations that are enormous or very, very small. You can have underdamped oscillations that are very enormous or very, very small. The size of it is not as important as things like what is the K constant of the spring relative to the mass and those kinds of ratios. So for underdamped oscillations, which kind of look like this, things start to oscillate and they keep on oscillating and oscillate for a very long time before it comes to a stop. This is true so long as the square root of K over M is larger than the damping divided by 2M. So in other words, if you think about this term here, if K over M is much larger than this thing, then you'll find that you end up getting lots and lots of oscillations. Basically, one way to think about this is that, well, if the damping constant little b is small, well then this is going to be less than this. And if that's true, then it's going to oscillate many, many times before it comes to a stop. So this is what's called underdamped oscillations. Lots of engineering applications of that. Sometimes we like to call square root of K over M the natural frequency. However, if the damping is, if this little b is large, then b over 2m might be much larger than the square root of k over m. So in other words, you might notice that if this is really big, well then you're not going to get the same kind of behavior out of this thing. Instead, you're going to end up with something like this, something that doesn't even really oscillate, or might oscillate once or something. So this is what's called overdamped oscillations. And it's an interesting thing, because if b is very large, if little b is very large, and if this is larger than that, then square this thing. That means that this is larger than that, which means that we're taking the square root of a negative number, so it's imaginary. And so you'd think that would just, destroy any attempts to understand what the heck is going on. But there's a little trick that you can do, which you may or may not have seen, but there's a trick where, I don't know if you guys have seen this formula, but cosine of theta turns out to be equal to e to the I theta, where I is the imaginary, plus e to the minus I theta divided by 2. And the understanding here is that e to the I theta is equal to cosine theta plus imaginary times sine theta. If you haven't seen this yet, you will at some point. And so this is kind of an interesting equation. So, like, for example, if you wanted to solve for cosine and isolate that, if you substitute this into here, this does in fact turn out to be cosine. So what's interesting is if the thing inside the cosine is imaginary, what happens? Excuse me. All right. So what we can do is if b here is imaginary, let's define a b0 that isn't imaginary. So let's say that b is equal to imaginary times b0, right? And so that's going to be equal to this, right? Because if little b is much bigger than, if this term is much bigger than that thing, that means the square root. Now we've got a square root that's a positive number. Everything's fine now. Universe is back to normal. So we get an imaginary number times the square root of something that's positive. All right, that seems less scary than it was before. All we did was sort of define this thing. And so now what we can do is we can stick this into our equation, right? Because cosine of big B times t equals cosine of I b0 times t, right? And so so this is our angle, and so this is e to the I theta, right? Theta, don't worry about it as like an angle. It's just typically it's the variable that we put in there. And so we get this plus e to the minus I times blah, blah, blah. Remember, our b0 is an actual real number. And so this is interesting because I times I, right? Imaginary times imaginary. Well, imaginary is the square root of negative 1, so square root of negative 1 squared is just minus 1. And so this becomes that. And now you can kind of see why we don't get oscillations. We just have like this decaying thing, we have this growing thing. So there you go. So we get something like this. And so when you sub this into here, that multiplies by the exponential we already had, and you get these sorts of things. So at the end of the day, all the oscillation stuff disappears, right? There's no cosine, there's no sine, there's nothing like that. But you do get these kind of decaying solutions, right? I mean, it looks like it might be a growing solution, but if you rearrange it some, you'll see there's a minus sign out front of these things, and so they both decay. So yeah, so it's as long as you think about it in these terms and remember that interesting formula, you can get it to look like something that's not the scariest thing you've ever seen. All right. So we talked about underdamped. We've talked about overdamped. Now there's a third situation called critically damped, which is kind of halfway in between overdamped and underdamped. And so that criteria is if b over 2m equals k over m. And so when you do that, you stick that into this formula, well, you get k over m minus k over m equals 0. And so that simplifies this formula immeasurably, and you just get this thing. So again, no oscillation. Very simple. This is the critically damped solution. And from an engineering perspective, the reason you might want to use this is that for an overdamped system, let's imagine you have a train that's carrying passengers or something that's arriving at a train station. I know in the United States we don't often have trains anymore, which is sad. But let's imagine that there's trains that we ride all the time. And you're arriving at the station, and you're coming to a stop, and there's some kind of a damped spring system that brings the train to a stop at that last like foot or something. The problem is that if if you want to slow the train to a stop, what you could do is you could make this drag coefficient very large. You could make a little b very, very, very large, so that you very rapidly bring the motion to a stop. The problem with that is that you've got passengers on board, and if this thing kind of drifts and then hits this spring system and comes to a stop, well, then everybody's going to lurch and be jarred from the experience. So you want it to be as gentle as you possibly can as you're doing that. But the other thing that you don't want is you don't want to have the damping so small that this train drifts in the station, it connects with some system, and then it sort of oscillates back and forth for like 5 minutes. And all the passengers have to wait there for the thing to stop oscillating because the damping is so small they can't, it's still wiggling for a while. So you don't want that either. You want something that is pretty much exactly in the middle. So that's kind of the best example I can think of. Another example I can think of is it's a little bit like these doors. I know this is not like a perfect spring, one-dimensional spring situation, but when you open these doors, you want the door to, you want there to be some kind of force that is encouraging the door to close, but you don't want it to slam shut. You also do not want the door to be so hard to open that it takes some incredible amount of force to open it. And so you're looking for kind of a sweet spot in terms of, there's probably a spring in this thing, honestly. You want a sweet spot between the stiffness of the spring, the damping, and so that it's just so it feels natural to open that thing up. There's probably other examples of where critical damping is important in engineering situations. I would love it if you guys could come up with an idea for when it might be appropriate. I honestly have trouble coming up with more than 2 examples, but I'm sure there's other examples out there that I just haven't thought of. So I'd love it if you guys could send me an email with an idea along those lines. All right, so the last part of this lecture is talking about how does damping affect the energy in an oscillator. So if there wasn't any damping, the oscillation would keep on going on and on and on until the end of the universe or whatever. So let's think about how does this energy decrease. So energy is conserved, which means that the initial kinetic energy plus the initial potential energy adds up to a constant, even if there's damping, because what that means is that as time goes on, you can lose energy to friction and damping and things like that. But if you add that energy to your remaining kinetic energy and your remaining potential energy, that should add up to the initial energy that you had. So there's kind of a trick you can do, and I'm not smart enough to come up with this trick, but this is helpful for the homework and helpful for the worksheet for lecture 21. But what you can do is you can say, well, I'm going to take the total energy here, which is a constant, and I'm going to subtract from it how much energy has been lost to friction. And that's going to give me my kinetic energy plus my potential energy, my remaining kinetic energy and my remaining potential energy. So we're not yet to the trick here. Here's the trick, is that if you think about this thing oscillating back and forth, there are moments in that motion where the thing comes to a stop and then it turns around and goes back the other way. At that moment where it comes to a stop, what do you know? The kinetic energy is going to be 0, because the kinetic energy is just 1/2 mv squared. So what you can do is you can say, well, the remaining energy at that spot where the kinetic energy is 0, that's also where it's going to be have the most displacement. And so what you can say is that when this is 0, the potential energy stored in the spring is going to be at maximum, and so that's going to be at its maximum displacement there. And so you can sort of say that the remaining energy in the system is all in potential energy at those moments, and that depends on how large of a displacement that you have that's left. Now what's interesting is that we know what x is as a function of time, right? We spent a long time figuring that out. X is t equals a times e to the minus something times like a cosine or a sine function. And so we know what that function is, and the maximum of that function is basically whenever that sine or cosine equals to 1. So the maximum of this thing is going to be the amplitude times that exponential. Now, I've squared the amplitude here because I've got a square there. Here, originally there was a b over 2m times the time, but I've got rid of the 2 because we're squaring it, right? So the square of the exponential adds an extra 2 to the top of this thing, those two things cancel. So this is what you end up with for the remaining energy as time goes on, right? Because as time marches on, you're going to get less and less because this exponential is going to get closer and closer to 0. So this should be very helpful for doing these types of problems, both the worksheet and on the homework. The last thing I want to say about this is that we often will rewrite this in terms of some kind of time constant. So this t0 is, the amount of time that it takes for the energy to be 1 over e of what it was originally. And so t0 in this case is going to be like b over m or something like that. But sometimes there can be cases in which you don't know b and you don't know m. You don't know either one of them, but you might know what the ratio is because you can figure out this t0. So this is often a convenient way to do these problems, because a lot of the times they're going to say like, oh, well, how many oscillations does it take for you to lose a certain amount of energy? So m over b. So I hope this is helpful as you consider how to do those problems. If you would like more information on simple harmonic motion, these videos are pretty good that you can click on and watch. I think I've excerpted some of them in earlier slides. The last thing I want to say is about the worksheet. So I'm going to turn this down a little bit. But the worksheet centers on the question of how do astronauts measure their mass in space. And the paradox here is that if they're in space, they are in a weightless environment. And so how do you measure your weight in space? Well, you don't measure your weight in space because you're weightless, first of all. How do you measure your mass in space? Well, if you take a bathroom scale on the International Space Station, you try to stand on it, it's going to measure 0 because there's nothing that's pulling you to the floor. Everybody's just kind of there floating along. So how do they measure it? Well, they use a contraption like this.
Machine here that's got a known spring constant and a known damping ratio, and we've got it set up here, and I'm going to release it, and you're going to see it's going to oscillate at some frequency here, and we're going to go through a calibration. It's going to release. You see it's got a very predictable frequency here, and it's calibrating itself now. And we have an electronics unit over here that gives a readout of the weight, and right now, like I said, it's calibrating. So I'm going to reset it, and we're going to change it to working mode to measure the body mass. I'm going to get on it, and now since we've got my mass on it, the frequency is going to be much less than it was during the calibration. And it will take that frequency, the known spring constant and the known damping ratio, and calculate my mass. So here we go. And after about 4 calculations, we have a readout. 81 kilograms. A little more than that, 81.5 kilograms.
So the thing to notice about this is that when the astronaut is on the contraption, it's oscillating much more slowly. And the reason it's oscillating much more slowly is because there's much more mass attached to it. So the period we derived earlier was 2 pi times the square root of the mass divided by the k constant. And so if the mass is larger, the period is also going to be larger. And sure enough, it was I don't know exactly how much it was, but to my eye it was something like 3 seconds was the period with the astronaut attached to it. Maybe it was like 1 second when the astronaut was not attached. And so we want to come up with this same number and see what we can get using the equations we've been talking about in today's lecture. So just kind of in a plot, the blue line here is without the astronaut, so that's oscillating very quickly, but with the astronaut it's much more slowly than that. And so this blue line is important because we need to use it to figure out what the spring constant is of the system. If I tell you that the mass of the device without the astronaut is 10 kilograms, you can use that information to figure out what the spring constant is. And then once you know the spring constant, you can use that with the astronaut's motion to figure out the unknown, which is the astronaut's mass. And this is a very important thing to measure because in space, your bone density decreases over time. And so by the time that you come back to Earth, if you've been up for 6 months or a year, your bones are very, very frail. The weightless environment is just not a very healthy thing for people. And so they have to monitor this very closely, and one of the ways they can do it is by looking at how your mass changes over time when you're up in space. And so this is a very important thing to measure for the astronaut's health, and with your help we can figure out what that mass is. One last thing is that if you watch the video very carefully, you'll notice in the very beginning he says that it has a known damping constant. And so that's interesting because in the last part of this worksheet, I'll tell you what the damping constant is, and then you'll have to recalibrate what the astronaut's mass is. And so, because remember, we were able to show that the period of motion does depend on what the damping is. And so we can try to factor that in so we can get the most accurate measurement of what the astronaut's mass is that we can. This turns out to require the quadratic equation, which is one of the few real-world applications of quadratic equation. So the next time somebody asks you, like, when are we actually going to use the quadratic equation, you can tell them, like, oh, well, when you're on the International Space Station measuring your mass, of course you need the quadratic equation. So there you go. There's your real-world application. I don't know real world, but at least real space. There you go. All right. So that's about all I had for this lecture, but hope this was helpful.